Okay, let's just dive right into this. Imagine releasing a highly technical open source project and then watching it absolutely explode. We're talking racking up over 23,500 stars and more than 2,200 forks on GitHub. In the developer community, that isn't just a warm reception. That is massive, undeniable community validation. It tells us right off the bat that this project has really struck a chord and it's solving a major, real world pain point that developers all over the globe are actively struggling with.
So, welcome to today's Explainer. I am so thrilled to guide you through the repository behind those staggering numbers, DeepSeek-OCR. Specifically, we're going to unpack the mechanics behind their context's optical compression. Now, if you've been following the AI space at all lately, you know that integrating vision, actually getting a large language model to see and process images efficiently, is easily one of the core challenges of modern machine learning. Images just take up an immense amount of data, right? And figuring out how to feed that dense visual data into a text-based brain without completely overwhelming the system, well, that's exactly what DeepSeek-OCR was built to solve. Here's a quick look at our roadmap for today. We'll be covering 1. The phenomenon, 2. Optical compression, 3. Native and dynamic resolutions, 4. Inference deployment options, and finally, 5. Community evolution. All right, let's kick things off with Section 1, the DeepSeek-OCR phenomenon. The project's official mission statement is actually incredibly simple yet super ambitious. It's to explore the boundaries of visual text compression. And really, this hits the nail on the head for the fundamental problem they're tackling. When you hand an AI an image of a document, it has to convert those pixels into a format the language model actually understands, which is tokens. But it's a Goldilocks problem. If it creates way too many tokens, your model slows to a complete crawl, or worse, just runs out of memory. If it creates too few, the AI starts hallucinating or misses critical text entirely. DeepSeek-OCR basically exists right on that boundary. It's trying to compress visual information as densely as possible without losing any of the actual textual context hidden inside the image. Moving right along to Section 2, Context's Optical Compression. So, the absolutely crucial architectural shift here is what they call the LLM-centric viewpoint. Historically, a lot of optical character recognition, OCR, was focused purely on computer vision. The whole goal was just making the best standalone image scanner. But DeepSeek-OCR flips the script entirely. They investigate the role of vision encoders based purely on what the large language model actually needs. It's no longer just about seeing the image perfectly in a vacuum. It's about translating that image into tokens so incredibly efficiently that the language model can instantly understand the visual data. By compressing the optical input specifically for the LLM's context window, they are drastically reducing the computational load. It's a real game changer. Which brings us to Section 3, Native and Dynamic Resolutions. Now, DeepSeek-OCR doesn't try to force some rigid, one-size-fits-all approach. Look at this spectrum for their native resolution modes. If you just have a simple, straightforward image, you can use the tiny mode. It operates at 512 by 512 dimensions and costs the model a mere 64 vision tokens. That is incredibly lightweight. But if you're dealing with a dense, complex document, you can scale all the way up to their large mode at 1280 by 1280, utilizing 400 vision tokens. Scaling from 64 up to 400 vision tokens matters immensely for compression. It literally puts the power right in your hands to balance speed against visual clarity, making sure you don't waste precious compute on simple images while still packing the horsepower to read dense text when you really need to. And this perfectly sets up their next level of innovation. We just looked at native resolution, which uses those fixed dimensions and fixed token counts. But DeepSeek-OCR also features a dynamic resolution mode, which they playfully named Gundam mode. Why Gundam? Well, just like the famous modular mechs, it literally pieces different components together. Gundam mode dynamically combines variable token sizes, specifically an n amount of 640 by 640 blocks, and pieces them together with a 1024 by 2424 overarching context block. It's such a flexible approach. It allows the model to dynamically adapt to unusually shaped documents or weirdly structured visual contexts, completely breaking the limits of a traditional fixed square resolution. All right, let's look at how to actually use this in Section 4, Inference Deployment Options. Getting this running is remarkably straightforward. First step, you literally just clone the DeepSeek-OCR repository. Second, you set up your Conda environment. And as a quick heads up, it is highly recommended to use CUDA 11.8 and PyTorch 2.6.0 to get that optimal compatibility. Third, you install the VLM package, specifically version 0.85, via their provided wheel file. Now, here is a really awesome detail from the developers. If you want to run VLM and Transformers code in the exact same environment, you don't have to worry about those nightmare dependency conflicts that usually plague AI setups. They've actually ensured the whole shebang works seamlessly side by side. So once you're all installed, you basically have a practical choice to make between two main inference tracks. On one side, you've got VLMM inference. Think of this as your high-speed lane. It's designed specifically for high concurrency and streaming outputs, making it absolutely ideal for production environments or if you need to process massive stacks of images in real time. On the other side, you have standard Transformers inference. This is more of your flexible lane. It's perfect for batch evaluation, running standard benchmarks, or if you're just looking to tinker with the model's inner workings. The choice entirely depends on whether you're optimizing for raw speed or for flexible research.
And hey, speaking of raw speed, I really want to emphasize this performance metric for a second. 2500. When you use that VLLM inference track to process PDFs on a single A140GB GPU, the model achieves a massive concurrency rate of roughly 2500 tokens per second. Let that sink in. By perfectly compressing the visual data down to only what the language model actually needs to see, the system just screams through PDF documents at blinding speeds. This isn't just a cool theoretical breakthrough. We are looking at a highly optimized, completely production-ready powerhouse. Which leads us to our final section, number 5, community and rapid evolution. If you want a testament to the speed of open source innovation, just look at the release logs for this repository. DeepSeek-OCR officially launched its first iteration in October of 2025. Just days later, still in October 2025, mind you, it was officially supported upstream by the VLLM team. The community moved incredibly fast to get this model integrated into one of the most popular inference engines on the planet. And that rapid feedback loop, it culminated just months later, in January of 2026, with the launch of DeepSeek-OCR 2. They are iterating, improving, and releasing at a breakneck pace, and it's largely thanks to the enthusiastic, hands-on collaboration of the open source community.
Which really leaves us with this final thought. We've seen exactly how compressing visual data through an LLM-centric lens drastically reduces token bloat. We've seen those incredible 2,500 token per second processing speeds and the awesome dynamic flexibility of Gundam mode. The tools are out there right now, perfectly packaged in an open source repo. So how will context optical compression fundamentally change the way you integrate vision into your own AI workflows? I really hope this explainer has sparked some new ideas for you and leaves you eager to clone the repository and explore these boundaries for yourself. Thanks so much for joining me today, and keep building.